Hi, welcome to the analysis, design, and simulation of Flyback. This is part 10, uh, and it will include topics on the input filter, which was part of chapter 10, actually chapter 9. And the last lesson, which was I believe 9, I showed a procedure where you can design a filter to satisfy a mil standard 461, where they specify if you have a certain frequency range, it specifies a certain current that you're allowed. Okay, so it's a continuation with that. I showed the procedure how to design it, but I want to get a little bit more detail as far as the filter that you can design and the type of signals that you're going to be actually attenuating. Okay, so topics that I'm going to address is shown here. Why is a good input filter important? So I want to touch base on that, the reasons. And then the second is the type of noise. What type of noise does the input filter have to filter out or attenuate? Okay, so why do we want a good input filter? Okay, so here's a little schematic. Okay, and this is trying to illustrate the reason why. Okay, and the projects that or the switching power supplies that I designed, there are basically DC to DC converters, and they're meant for space application. So typically on a spacecraft you will have a bus. Okay, usually a satellite will have the solar cells, and when the sun is shining on the solar cells, they charge the batteries, and during the night, and if they're let's say collecting data, you're operating off of batteries. Okay, so your bus is really the batteries. Okay, not let's see, let me redo this. This seems to be a little lag in the software. Let me shut down some of the other softwares that are running. It's acting a little jittery here. Hang on. These two usually slow it down. Okay, let's try that again. See how it works. Okay, so it's a battery. Okay, and let me add one more thing here. And all power sources have a Thevenin resistance. Okay, so this, let's assume that it's 0.1 ohms. Okay, so like I said, this is a battery or a voltage source. Okay, and let's say typically you'll have a bus system, and on that bus system you'll have other equipment. Okay, so in this case I have 24 that is connected to a power supply, and we usually call these LVPS, which stands for low voltage power supply. Okay, and they're converting the 28 volts down to, let's say, 12 volts, 5 volts, and so forth. In some cases 3 volts. Okay, but you can also have other equipment that go to other systems in the power supply or in the spacecraft. Okay, and let's suppose that you have a very sensitive piece of equipment connected on another side or close to the LVPS, but they're connected in parallel. So you would have this system here connected. Okay, so basically you have this circuit board or sensitive circuit that is, may be sensitive to noise. Okay, and basically it's connected in parallel with this low voltage power supply and the bus system. Okay, so what's the big deal? Well, if you have a switching power supply, okay, if you have watched the other videos, you know that when the MOSFET is turned on, you have a current that builds up. Okay, so basically you have a little ramp and the current actually builds up. Okay, and the example that I've been using a power supply that's 6 watts. So in this case I'm dividing it by 28, so you get an average of 214 milliamps. Okay, and just to guesstimate it, you can multiply that times 4, so you can estimate that the peak current would be 857 milliamps. So it would have a peak current of 857 milliamps. Okay, and then it switches down pretty fast. Okay, so this would be the current that you would see through the positive side, and then it would return in this direction. Okay, now the waveform would look like this if you do put a current probe on either the positive and you measure the current either on the positive or the neutral side. You'll get a current that will look like that, like this. Okay, so this is the transient. Okay, now these edges have a lot of harmonic contents. Okay, now remember this is running at 100 kilohertz. Okay, but in reality you have a lot of harmonics that extend up in frequency. Okay, so if you do a FTT, a fast Fourier transform, okay, you'll see that this signal has harmonics that extend way past 10 megahertz. Okay, here at the fundamental frequency that's operating, okay, you actually have 323 milliamps at 100 kilohertz. And let me see if I can zoom this. Okay, make it a little bit bigger. Okay, see right there's the peak, and then the second harmonics is at 200 kilohertz. You have 136 milliamps. Okay, third harmonics you have should be 93 milliamps. Okay, yeah, it's about 93. Should be 93 milliamps at 300 kilohertz and so forth. So if you notice, it's got harmonics that extend all the way even past that. Okay, and that can be a problem because those harmonics or those currents are actually riding or actually polluting your bus. Okay, so basically you have a bunch of harmonics, okay, that are being flooded or being polluted, and if you have other sensitive equipment, that differential crud or noise will affect any other systems that are connected in parallel to the bus. So it's imperative that you put a input filter in between. Between your LVPS and your bus. Okay, so that's the purpose, that you want to be sure that you contain this noise. You want to contain it within the low voltage power supply, and you want to keep that from going in that direction. Okay, you want to attenuate whatever harmonics you have here. You want to attenuate it and have or keep your bus system as clean as possible. Okay, so that's the reason that a good input filter is important. Okay, now let's treat this here now. What type of noise does the input filter have to filter out? Okay, well, basically there are two types of noises. Okay, the first one is differential mode noise. Okay, and then the second one is the common mode noise. Okay, I'm gonna discuss first in this video differential mode, and I'm gonna give an example. Okay, and basically the example that I will give is basically what I've already been using, is noise in the primary of the flyback with high peaks, currents, and fast switching edges generate high frequency harmonics. Okay, so basically your power supply, these signals, these currents, let me write it in red. Okay. Okay, diff. That's a diff noise. And here's a diff noise. Okay. So basically the current that is generated by the primary side of the flyback, they turn out to be differential noise. Okay. Now, which brings me to how do you filter that out? Okay. Well, typically, to filter out a differential mode, okay, you will have your power supply, your bus. Of course, you're going to have your R Thevenin of the bus. Okay. And for right now, I'm going to say that this is neutral. And this is your positive. Okay. And typically you want an inductor and a cap. Okay. Now your noises, your differential noise, can actually be modeled by a current source. In this case, let me draw it this way to be consistent with this. In other words, I'm saying right here, let's see, okay, I'm saying that the current is going in from the positive and going out from the negative or the neutral side. So in this case, I'll draw this in this direction, which means the I diff, okay, and the I diff flows in this direction. Okay. Okay. So basically, this is a very simple model. Okay. Now, if you think of it, here's and keep in mind your harmonics is at 100K, and then 200 and so forth. Okay. So you want to offer in this direction, looking in here, you want to offer an impedance that gets smaller as your frequency gets higher. Okay. So let's set that. You want an impedance that gets smaller with frequency. See. Okay. So let's think about that. Well, a device that does that, if you look at a capacitor, you'll see that 2 pi FC. Okay. If you notice, as the frequency goes up, okay, your denominator gets bigger. The reactance, or the capacitor reactance, which is in units of ohms, okay, X of C goes lower. Okay. So what happens is, as these frequencies goes up higher, this impedance are actually being shunted by the capacitor. Okay. So this is seeing a low impedance, and it tries to go here. Okay. So that's why we use a cap. Okay. Now, you also have an impedance here. Okay. Okay. So now that brings me to the second statement. You want an impedance that gets larger with frequency. Okay, so let's think of that. So an L is 2 pi FL. Okay, so as your frequency goes up, the X of C goes up as well. Okay, so in this case, let me go ahead and F sub C goes higher. No, I'm sorry. Gets smaller. Okay. Okay. And X of L gets bigger. Okay. So now we have these two statements. Okay. So basically this current, okay, it tries to follow the path of least resistance. It's a noise. Okay. So it sees this impedance here, and as the frequency gets higher, this impedance gets bigger while this impedance gets smaller. So instead of it trying to flow through this, through the inductor, it will instead flow through the capacitor, okay, while at the same time this goes up. So basically your bus is seeing a higher impedance. It's being disconnected in a way at high frequency, or it's seeing a higher resistance between this node and this node. So basically you're keeping the current noise or the diff mode from reaching back into this side. Okay, so that's why we use this little filter, generally a inductor and a pi. Okay, and generally this is good enough. However, there's a slight problem that when you're designing a power supply or an input filter, you typically want both the positive side and the neutral side. You want the impedance balance. Okay, and what do I mean by that? Well, you want the impedance to have the same impedance on this side as on the neutral as the positive. So one of the solutions, or one of the things that they do, is this inductor, they actually split it up and they insert another inductor on the bottom side. Okay, once you put an inductor on this side, if you look at the impedance looking into this leg and looking into this leg, they're balanced. Okay, and one of the reasons is when it comes to common mode range, if you have an unbalanced positive and neutral, common mode can be converted into a differential mode. And if you use a balanced input filter, it prevents the common mode from being converted into a differential mode. But basically that's what they do. And another thing is that they do is they couple these inductors. Okay, now that brings me to another topic. There's actually two types of coupled inductors. This is an inductor, coupled inductor, looks like this, and they'll be labeled like this. Okay, and they'll have the little dot on the same side. Okay, so when you see that, this is a common mode inductor. Okay, and its purpose is to filter out common mode noise. Okay, and then you'll see inductors that look like this. There'll be a dot on one side and a dot on the opposite side. Okay, and this is a diff mode inductor. Okay, and its purpose is, as you may guess, is to filter out diff mode. Okay, so for right now I'm going to concentrate on diff mode. On the next video I'll cover a little bit of the common mode. Okay, but let's explore that. Okay, so just remember, keep in mind, if they're on the common side, the same side, it's a common mode. If they're on different sides, it's a diff mode. Okay, this is the one that typically you want to use, okay, to filter out diff mode. Okay, and let's see how the diff mode and the common mode works. Okay. Okay. Now in this site, here's a little toroid. Okay. And this is a primary. And what I did is I'm putting the diff mode here. A little source. VDiff. Okay. Or actually, hang on. Okay, let's. I'm going to do a little bit of a hand wave. Okay, I'll say that this is a diff mode, although it's a voltage mode, but it's a little bit easier to show, or for illustration purposes. Okay, so let's say this is a voltage source. It's a diff mode. Okay, so that means you're going to have a I diff going into the positive. Okay, and it comes around, and then it flows through your load, and then that diff I diff goes into the dotted one. Okay, and then it comes out. Okay, so if you were to use the right hand rule, okay, and if you were to grab this piece of wire, you wrap your thumb on this side, on the left side of the wire, with your four fingers, and you wrap it around. Your thumb is in this direction. Okay, and if you wrap it around, when you wrap it around, the direction of the wrap shows the flux, and if you wrap it around, the flux goes into the core. That means that the flux is going to go in this direction. Okay, when you wrap your right hand on this winding. Okay, so that's what the right hand rule says. Okay, so let's go ahead now. This is one winding, and you follow this path. Current is flying through here. Okay, now current is going through here. Now your thumb is pointing up, and it's on this side, and you have your other four fingers on this side. Okay, and since you're wrapping from this side to this side. Okay, so that means that the flux is in the same direction as this, so you have a continuation of the flux. Okay, so you have flux is being added by this winding, okay, in that direction, and you have flux being added from this second winding. So they're both in the same direction, so they add up. Okay, so that's good. So this is what is called a diff. Okay, of diff mode. Okay, and you can see that these are on the opposite side. Okay, so let's pretend that we break the wire, and we hook this wire to this side, and then this we connect it to this other side, which is illustrated right here. Okay, so that changes how this toroid works. Okay, just by switching these two wires, the operation of the toroid has a drastic change. Okay, and let's see why, or try to examine that. Okay, so in this case, we basically use the same rule. You got the diff signal coming in here, and you got the current, and you wrap your hand around this, so you have your thumb on this side 4 fingers here. So again, when you wrap it, that shows that the direction of the flux is going in this direction. Okay, same as we have in this situation. Okay, so now let's go follow the current. So now the current, instead of going to the top or the dotted, it goes into the non-dotted. Okay, so now here you have to maybe illustrate it or use your imagination a little bit. The winding is in the back. Okay, so now your thumb is on this side and your fingers are on this side. The current is flowing that side, but remember it's in the back side, so that means that the flux is going in this direction. Okay, so now this winding generates a flux in one direction, but then you have this other winding generating the same flux in the opposite direction, and they're both in equal. So this means that the flux cancels. Okay, that's very important. What does it mean? Well, if you don't have any flux, it means you don't have no inductance. So in this case, if you were to put a differential signal in here, instead of having attenuation or having an inductance through here, this is just a piece of wire. It has no inductance. It doesn't work. It would not filter any differential output. Okay, so let me go ahead and you can redraw this like so. Okay, so this would be what is called, okay, this is a common mode. Inductor, which is here, shown here as well. It's a common mode inductor. Okay, so the main ideal is that the common mode does not affect differential noise. In other words, does not work, or does not affect, or it does not do anything. It just acts like a piece of wire. Okay. Okay. So let's illustrate that. Okay. So let's do a simulation, a SPI simulation. That will show that effect. Okay, so I have a little circuit here. Okay, and let me just show. This would be your differential signal. Okay, I have my positive and I have my negative, and I have my inductor, and I'm using a 1 millihenry inductor on top and a 1 millihenry on the bottom. And then I've used this is the K element, and this is the K element that is used to define that L1 and L2 are coupled, and then this last one means the coupling coefficient. We will assume that it's 100%. So we will put a 1. Okay, basically saying that they're tightly coupled. It's a perfect inductor. Okay. So what we do is, if you notice, the current will come in this direction, the dotted. Okay. And in this case, current will come in to the dotted. Okay. And then goes through the resistor, and then it comes back into the non-dotted on the neutral. Should come in here to the non-dotted. Okay. So we have that. Okay. So this is a common mode inductor. Okay. So if we have inductance, okay, this should have basically no attenuation. So basically, if we put 1 volt of noise here, I should have 1 volt of noise here. Okay. So basically, I would have a signal that would attenuate. But since it's a common mode, it doesn't attenuate, or at least that's what the analysis that I just did showed. So let's see if it works. So we run an AC, and if you notice, 0 dB means that I have a signal that's 1 volt, and that 1 volt is not being attenuated. Basically, it's 1 volt throughout the entire frequency. Okay, so basically it's doing nothing. It's just a piece of wire. So basically I can take these out, just put a little wire from here to here, and to here to here, jumper it because it's the same effect. Okay, so now let's try something else. So let's change these 2 connections. Okay, let's connect this and reverse them. Okay, we'll connect this to this other side. Okay, so now this should be a differential mode. Okay, so now I should see, or I would expect to see, attenuation as your frequency goes up. And there you go. You have attenuation. Okay, so let's go ahead and copy that so we can see both effect at the same time. Okay, I will copy that. Okay, I will put this back to the original connection. Okay, and I will rewrite this, say that it's diff. Diff out. Okay, and I'll do I'll go ahead and say that this is the diff out and display it in the same graph. So here I have a common mode and differential. So let me change that. Bring this here. There. So this is your diff, and this is your common. Okay. Plot both of them. Hang on. Okay, I see the simulation error that I did. Okay, I copied it, and these are still saying that L1 and L2 are coupled. Let me change this to L3 and L4. Okay, let's try it again. There. Okay, great. For a moment there, I thought I was having another senior moment. Seems like I'm getting more senior moments as I get older. But anyway, here's the common mode. So basically no attenuation. And if you notice right here, the red, you have attenuation. Okay, so basically the SPICE analysis confirms this analysis, which is basically just using your principles of your right hand rule. Okay, you can draw this out and try it for yourself, and then you can also do the simulation. Now, anybody that wants a copy of this my notes, you can email me, or if you want a copy of the SPICE file, you can email me as well. In the next lesson, I'll go ahead and do a simulation how the Diff the common mode filter works, and do some other simulation tricks. If you have any questions, feel free to drop me an email, either for more information or for SPICE files.